Dear students, this is Dr. Vijay Vasudevan. In this video, we will discuss chapter 13.2, which is classical partial differential equations and the boundary value problems, the following with number 13. So let's start with this one. The introduction. For the remainder of this and the next chapter, we will be concerned with finding product solutions of the second order partial differential equations given in this form. The first one is called a heat equation. Call it one-dimensional heat equation. And we are going to derive this one. Okay. Next, this is one-dimensional wave equation. See here, for u second derivative with respect to x partially differentiated, isn't it? And there is the constant k. In the right hand side, it is u for derivation with respect to t. But in the one-dimensional wave equation, both the variables u have been differentiated by both the variables twice. Second derivative of u with respect to x, and the right side second derivative of u with respect to t, partially. So there is the coefficient with the second derivative of x. Okay, and third one is called the Laplace equation. These are most popular equations which are in partial differential equation form, available in engineering applications. Okay, so we are going to find the solutions of these kind of problems in the next chapter. Which falls on week 14. Now we will get introduced to these equations and as a boundary and initial conditions. Okay, some information has been given here. So the first equation is called the one-dimensional heat equation. Another one, second is one-dimensional wave equation. Third one is Laplace equation of two dimensions. What do you mean by here dimension? Though there are two variables u of x comma t, u is a function of x and t in first and second problems. The first problem, heat equation, u is the temperature at any time in the rod. If you take a rod, heat is assumed to be moving in this side, so which will be one dimension, and another variable t stands for only time parameter, isn't it? Not the dimension x or y. Only one dimension x is available. Along the x-axis we consider the length of the rod. Another parameter t is time parameter, right? So this is called one dimension. So one dimension refers to the fact that x denotes the spatial dimension where t represents the time. The same for second equation. Second equation is one-dimensional wave equation. For the wave equation also, t is time, x is the x-axis. Okay, but the third one, Laplace equation, not a transform. Laplace equation, the solution u is a function of two variables x and y. Now we have both x direction and y direction. Therefore, this is two-dimensional Laplace equation. So any function that satisfies this equation, any function u that satisfies this equation. Find the function's second derivative with respect to you are getting a function f, which is a function of x and y. Find its double derivative with respect to x, and second derivative with respect to, sum them up. If the answer is 0, the function is called harmonic function. The function is called harmonic function. So this we will study under which condition this problem can be solved or what. Okay. Now here, what else is given in this problem? Okay, this is the Laplace equation. This is called a del. Del is del operator. You know what is it? Dou by dou x with plus I, dou by dou y j, only for two dimensions. So finding del dot del will give you dou square x, dou square over dou x square plus dou square over dou y square, and u will be multiplied, isn't it? That will be this one. This is called del square u, which is called Laplace equation. So that's why this is for three-dimensional case. For Laplace equation, that is for three-dimensional when u is a function of three variables. Now, by comparing the equations 1, 2, 3 with the linear second order partial differential equation, we can classify these equations as parabolic, hyperbolic and elliptic. Shall we try it right now? Parabolic, elliptic and we will try. Okay, this equation should be written in this form: k times u double x minus ut is equal to 0. So second derivative appears only in x, so the coefficient of u double x is k, and b there is no second derivative, and c is also so b square minus 4ac is defined. K and b is 0 minus 4 times k square. Since k square is a square term, it will not be negative, so the answer will be negative. Negative is less than 0. When it is less than 0, we call it something wrong, isn't it? U or C is also 0, so 0 should be multiplied here. Everything is 0 now. Okay, so the answer is 0. It's not, I forgot on this C. So b square minus 4 times a into c. C is 0, so everything is 0. When it is 0, it is called parabolic. This equation is parabolic. And similarly, you can classify this one. Write down this form. Second equation I am writing here. U double x and the coefficient is a square minus u double t is equal to 0. The coefficient of second, see, capital A is a square, b, the second derivation with both x and t will be there, isn't it? So b is 0 and c is negative 1. So can find b square minus 4ac. B square is 0 minus 4 a square and minus 1, so it will be positive 4a square, which says that this is positive greater than 0, so hyperbolic. When it's get positive, it is hyperbolic. Negative, it is elliptic. Equal to 0, then it's parabolic. Third one, you try, it will be elliptic. I'll leave this verification to you. So one-dimensional heat equation is parabolic, one-dimensional wave equation is hyperbolic, Laplace equation is elliptic, because here a is 1 and c is 1, b is 0. Therefore b square is 0 minus 4 into is negative. Negative, then it is obviously elliptic. Okay, the first one is 0, second one is getting positive, third one is negative. That's what given here in the statement. Check this one. Now we are going to discuss about the heat equation. So out of these three equations, first one represents heat equation, one-dimensional heat equation. Second one is wave equation. Third one is Laplace equation. The equation 1 occurs in the theory of heat flow, that is heat transferred by conduction in a rod or thin wire. This is our study. Heat transferred by conduction in a rod or thin wire. The function u of x comma t is a temperature at any distance x and at any time, at any given time t. Fine. Problems in mechanical vibrations often lead to the wave equation given in equation number 2. For purposes of discussion, the solution u, the solution of this equation 2 is u, is a function of x and t, will represent the displacement of an idealized string. So displacement at the distance x and time, any time t. Finally, the solution of solution of the third equation, Laplace equation, can be interpreted as the steady state, that is time independent, not dependent on time. Steady state temperature distribution throughout the two-dimensional plate. The first case, it is temperature through a wire or a rod in one dimension, isn't it? But third one, steady state temperature distribution throughout the thin two-dimensional plate, both in x and y direction. You will find temperature distribution. Clear? That is it. Now this is the figure of the case 1. Suppose that a thin circular rod of length L, total length in the x direction is L, so this left end is considered 0, right end is L, total distance L, isn't it? Has a cross sectional area. This part, this area is cross sectional area, right? And that coincides with the x axis on the interval 0 to L. It's given here, right? Suppose that the flow, so some assumptions. The flow of heat within the rod takes place only in this direction, x. Some assumptions have to be done to solve this problem. So the flow of heat is within the rod takes place only in the x direction. The lateral or curved surface of the rod is insulated. The surface of the rod is insulated so that no heat escapes from this surface. No heat is being generated within the rod. The rod has no self heat. No heat is generated within the rod. Only we are giving heat in this point, and it is moving to the right, we assume. Okay? And the rod is homogeneous, that is, its mass per unit volume P is considered to be constant. Per unit volume, the mass is considered to be constant. The specific heat gamma, the gamma stands for specific heat, and thermal conductivity K of the material of the rod are constants depending on the material. It varies, isn't it? So specific heat gamma and thermal conductivity of the rod should be constant and should be known. To derive the differential equation, partial differential equation for the one-dimensional heat equation, which is, we know that K times Uxx, this is small k, this is capital K, that is different, right? Uxx, which is equal to Ut. We need two laws of heat conduction. First one is the quantity of heat, we call it Q, is an element of the mass. In an element of the mass is equal, given like this. If mass is mass and gamma, specific heat, and U, temperature, U is temperature, U is U of x comma t, isn't it? If these three are known, you find the multiplication of these three, that is called the quantity of heat. This is the first law, called equation number 4. And U, where U is the temperature of the element. Next law, second law, the rate of heat flow Qt with respect to the time t. That is derivation of the Q, isn't it? With respect to t. Through the cross sectional indicated, through the cross section is proportional to the area of the cross section, and the partial derivative of the U with respect. So what they say is Qt is directly proportional to area multiplied by partial derivative of x. When you write this one equal to, there is a constant negative k, A times Ux. Why this negative has been used is given here. So these two are known rules that we are going to use here. So the minus sign in phi is used to ensure that Qt is positive for Ux is negative. When Ux is negative, this will make Qt is positive. So if Ux is positive, then it will be remaining negative. That is the purpose of negative here. So we have two equations now, remember. First one is, I am writing both the equations here. Q, isn't it? Q is gamma m mu. Another one, Qt is negative k A area and Ux, partial derivative of the temperature with respect to the x. Now, if the circular slice of the rod, circular slice means the slice you are taking from the rod, a small piece. Here it is x and the small distance, this is x plus del x. To take a small slice, very thin, but for study purpose we are making this distance, very thin slice we take, isn't it? Now if the circular slice of the rod shown between x and del plus x is very thin, and u, the temperature, can be as the approximate temperature at each point. So here the temperature, u of x comma t. What is the temperature here? U of x plus del x comma t. Now the mass of the slice m is equal to rho, the density, area of the cross section, and del x, the distance, this distance. So this is the formula for mass of this particular slice, the density of the slice, and it's a cross sectional area, and the distance del x, this distance. So when you substitute this m value here, you will get q is gamma and these three things together called as mass, isn't it? So this is our new equation now, 6. We are using this result here in the equation. Now qt, from this qt equation, furthermore, from the when heat flows in the positive x direction, from equation number 5, this is equation number 5, the heat builds up in the slice, in this particular slice. At this point, the difference at this point, the qt is this one, and at this end point of the slice, the qt is this one. What is the difference? Only k and a are same, only u multiplication of u is different, isn't it? Ux is different. Here ux is ux of x comma t for the first point, the end point ux of x plus del x comma t. This is the only difference. So when you this is qt, actually qt is equal to negative, subtract this qt minus this qt. So what do you get? Qt is k times a ux x plus del x comma t minus ux of x comma t. Actually this is your equation number 7. This is actually qt, this is equal to qt for this entire slice, thin slice. Okay. Qt, what do you mean by qt? The rate of the heat flow, qt, isn't it? So the rate of heat flow for the entire cross section slice is the rate of heat flow at the end minus rate of heat flow at the beginning of the slice. That is what given here. So this is our qt. Now we find qt from this equation. Differentiate q with respect to t. What do you get with respect to t? Only u is the function of t. Other circumstances. So qt from 6. What will be new qt? Gamma rho. This is rho a, area, del x, everything remains constant. U will be differentiated with respect to t. This is u t of x comma t. This is our equation number 8. Now compare 7 and 8. Compare 7 and 8. What we get is given here. That is the common terms a will be removed, isn't it? And when you equate 7 and 8, a is common, so it will be divided. And when you divide by all these terms, the equation will be looking like, see, when you equate 7 and 8, you will get this in the left side, this in the right side, in the left side you will write q. Equation number 7 on the left side, k a ux of x plus del x comma t minus ux of x comma t. In the right side, this equation number 8, gamma rho a del x of ux of x comma t. Now you take this gamma rho a del x, divide by this term on both the sides. So right hand side there will be only u of x comma t. That is the first derivation here. This is not u x, this is u t, derivation with respect to t. So what you get here is this one. Equation number 9 you will get when you differentiate this one, and when you divide by this term. So a will be cancelled, k over capital K over gamma and rho will be there. This term, when del x goes to limit del x goes to 0, is the definition of derivative. But it's already derivative form. Ux, one derivation has been already done, ux. So the conclusion will be, it will be a second derivation. So this term will be second derivation uxx when del x goes to 0, and the constant k over gamma p will remain the left side. The right side is ut of x comma t, right? That is ut. So this is the equation uxx, which is equal to ut with a constant small k, where k is this one. K is capital K over gamma rho, which is thermal diffusivity, which is a constant. So this is the equation of the one-dimensional heat flow. When you solve this one, you will find the temperature U at any distance x on the rod at for any given time t, isn't it? So this is what we are going to solve. So now next we will see roughly what is a wave equation. You are not deriving it right now. The derivation has been left to you. Wave equation, considering a string of length L attached on the direction of x-axis, isn't it? String attached, such as a guitar string has touched taut between 2 points on the x-axis in the beginning of x-axis and at the distance L. We are there is a string attached here, isn't it? You can pull it here and drop it. Then it starts vibrating. So this is called a vibrating string problem. Okay. When the string starts to vibrate, assume that the motion takes place in the xy plane in such a manner that each point on the string moves in the direction perpendicular to x-axis. So it will vibrate in this direction. This is displacement of the string, isn't it? So every point on the string will be vibrating. Vibration, we assume that will not occur at the end points. So now let u of u here is displacement, denote the vertical displacement of any point on the string. So if you take the string is vibrating like this, isn't it? This is our displacement u of x comma t for any distance x between 0 and L and for any given time t. Now we have following assumptions for this problem. The string is perfectly flexible. The string is homogeneous. Homogeneous always means that the mass per unit length is constant. The displacements mu are small compared to the length of the string, very small. Okay. The slope of the curve is small at all points. Okay. Curve is not highly curvature. A small curve will be there, very small. The tension T, if there is any tension at any point, it will be tangent to the line. It will be tangent to the point, and it will be like this in this direction. If there is a tension, the tension is large compared to the force of gravity. Okay, no other external forces acting on the string. These are the basic assumptions in this kind of wave equations. So this is the position, the distance x from 0 between 0 and L. There is some distance x, and this another distance. The difference is del x, is x plus del x. This part is there less. This portion has been expanded here and enlarged. This is dimensions one here. This is tension 1, tension 2. Okay, now I am not deriving this problem. I just show you derivation has been done, and you will get here that u double x is equal to rho over t comma u double t. So we want the constant to the left side. This will be t over rho u with respect to x u t t, isn't it? And this is a positive constant. We call it a square u x u t t. This is a one-dimensional wave equation. One-dimensional wave equation. And remember, T over T, and it is a tension, and rho is density. Now finding initial condition, that's important. When I give an example, you should know how to identify initial and boundary conditions for this all the three cases: heat equation, wave equation, and Laplace equation. How to identify the initial and boundary conditions from the given problem. Initial and boundary conditions. We start with initial conditions. The solutions of 1 and 2 depend on time t. 1 and 2, what they mean is heat equation and wave equation. Heat equation, for your reference, I write here uxx small k times uxs is equal to ut. This is equation number 1, isn't it? Second is a square uxx is equal to u double t. This one, wave equation. Now this is 1 and this is 2. Always throw this topic. We can prescribe what happens at time t is 0. There is we can give initial conditions. I see. If f of x denotes the initial temperature, you put t is 0 in u. U is the temperature, isn't it? At any point x and at any time t. When you call initial temperature, t will be 0. This is what you want. So u of x comma 0 is f of x. If you get in the problem any function which represents initial temperature, then it should be denoted as u of x comma 0, f of x. Next, what do you mean by derivation of u with respect to t? Displacement. Derivation of displacement with respect to time is velocity. So what's next one? Okay. On the other hand, for a vibrating string, we can okay. For this heat, it is not. For vibrating string, the initial u is initial displacement. Initial displacement. U of x comma 0 stands for initial displacement. For heat equation, it is initial temperature. And for displacement problem, that is for the vibrating string, when you differentiate the displacement with respect to t, it is velocity. Initial, this is initial velocity. If given as g of x, we take this one. All this happens in the interval 0 to L for x. Alright. And what else? We are the string could be plucked and released from the rest. When you release from the rest, initial velocity is 0, g of x is 0. When there is a statement, you release the string from its rest, initial velocity dou u by dou t, when t is 0, should be 0. Otherwise, you call it g of x, some function will be given. That is given here, x equal to 0, u in displacement is 0, here displacement is 0 at both the ends, here it is maximum. Okay. Now boundary conditions. The string in this previous figure, this one is secured to the x-axis at x equal to 0 and x equal to L. What do you mean by secured? When the word secured comes, x equal to 0, displacement is 0. When x equal to L, for any time t, displacement is 0. For a string problem, if you secure both the ends, it means that there is no displacement on both the ends. Isn't it? So u is 0, u is 0. Remember this statement, we need to use them. The function in equation number 10, continuous and constant. Okay. In general, there are 3 types of boundary conditions. There are 3 conditions. Okay, we call it this. I'm just going to the another point. First condition we call u. This is our u, isn't it? X comma t. When x is equal to L, you are at the right end, isn't it? So right end, temperature at the right end is mu 0, kept as a constant. Mu 0 is a constant. So this statement means that the temperature at the right end of the rod is constant. This is for temperature problems. And when you differentiate x with respect to L, what does it stand for? So condition 1 simply states that the boundary at the boundary x equal to L is held by some means of constant temperature μ0. But the same u of L comma T for vibrating string problem, it is 0. Vibrating is not allowed on both ends, isn't it? There is no vibration on both ends. Actually, we assume that. For wave equation, heat equation, it is constant. We consider μ0 is some temperature is remaining at the right end for any time t greater than 0. Condition 2, this statement, when you differentiate the u with respect to x, what you say at any end, x equal to L or x equal to 0 in the beginning, what you say indicates that the boundary x equal to L is insulated. When the word insulated comes, the u should be differentiated with respect to x, not with respect to t, right? When you differentiate u with respect to x, says that x is equal to L stands for the side, or right or left. X equal to 0, it means left side. X equal to L, it is right side. So insulated, that is no heat flow outside, isn't it? But the amount of heat per okay. Insulated means no heat is moving out from this side nor coming inside. That is it. So dou u by dou x at x equal to 0, x equal to L is 0 stands for insulated edges, isn't it? And third one, what is the third one? It's looking like insulated but not equal to 0. The same derivation, when it is 0, it is insulated, but there is some negative value. What is it? H times u of L comma T. L comma T is the temperature at the right end, and um is the temperature of the medium outside. The difference is negative. That means that the medium temperature is more than the temperature in the right end. So this is the rod. This end temperature is u of L comma T, and the outside temperature is um. When the um is greater than this one, you will find the negative, the result in negative. The difference will be in negative. That's why it's negative. That is the right hand. That is the meaning here. So third statement, third condition stands that given the next page. We can interpret the third condition to mean that the heat is lost from the right hand end. The heat lost from the right hand end of the rod by being in contact with the medium, isn't it? So when you differentiate u with respect to x, and x at the right end is negative h times u of L comma T minus um, isn't it? That's given here. H is greater than 0 and um are constants. So the heat lost in the right side is negative, isn't it? The left hand, it is positive, because when dou u by dou x equal to 0, you are in the left hand. Left hand, then it is 0 comma t here. This temperature is greater than the outer medium. So there is a positive in the left side. So this statement says whether you have lost temperature or you are gaining temperature. The change is so okay. That's a mean that we have discussed already. So from this information, we should have identified how to write the boundary conditions. Now we start with the first example of this problem, this type. Actually, this is problem number 1 in our account, problem number 2 from the textbook. A rod of length L coincides with this is the rod of length L in the x direction. Set up the boundary value problem for the temperature u. So temperature we are discussing, obviously the problem is k times k small k times u double x, which is equal to ut. This is one dimensional heat equation we know, but the question is how to write the initial or boundary conditions from the given information. The left end is held at temperature mu0. What is how do you notate it? Left end u of 0 comma t. The temperature u is u0. X is 0, you are at the left end. X equal to L, you are at the right end, isn't it? And the right end is held at temperature mu1. So it is u of L comma t is equal to u1. And the initial temperature u, x can be anything, but when time is 0, initial temperature is 0. These are the conditions. All these conditions are in the interval 0 to x less than L. This is the problem. This is the boundary value problem. Set up the boundary value problem. That's the question, isn't it? Boundary value problem. Now this is the known equation for which we have constructed the conditions. Initial condition. This one is initial condition. These two are boundary conditions, because these two are occurring at the end points of the boundary condition. This is occurring for the initial time, the initial condition, right? So this completes the boundary value problem of the one-dimensional heat equation. Okay, now in this manner we are going to set up the boundary value for the next case. A rod of length L, the same rod of this is the rod of length L, isn't it? In the direction of x, 0 here, L here, x is any point between this one. Now temperature u of x comma t at any point. Now read this one. So heat equation we should write k times uxx is equal to ut. What do you mean by uxx? Which is dou square u by dou x square is uxx. Dou u by dou t is ut, isn't it? Fine. There is heat transfer from the left end to a surrounding medium. It means that the left end heat is more than the surrounding medium, so it's positive. So how do you write? Dou u over dou x at x is equal to 0 is h times u of 0 comma t minus um, and um is given as medium temperature is 20. So um is 20. In the next we will write h u of 0 comma t minus 20. This is dou u by dou x, that is ux at x equal to 0. Okay, now this is the first boundary condition. Now what else given? The right end is insulated. Insulated, the derivation is 0. Dou u by dou x at the right end, x equal to L is 0. X equal to L, it is 0 for any time, isn't it? For any time t greater than 0. So second boundary condition, when x equal to 0 and x equal to L, it will be boundary condition. For time equal to 0, it will be initial condition. The initial temperature is f of x. Initial temperature t should be 0. Temperature stands, u stands for temperature. In x comma 0, t is 0 is f of x. This is initial condition. X in the interval 0 to x less than L, any time, isn't it? So that's the complete problem. This is the equation of the this is one dimensional heat equation, and these two are boundary condition, this one is initial condition. We are done. One more problem of the same case. We'll conclude this chapter. And a string of length L coincides with the interval 0 comma L. So this is the string of length L from 0 to L, isn't it? Along the x-axis. The displacement at any point. This is x is u of x comma t, isn't it? So the equation is u double x is equal to u double t multi this constant is a square. Okay, and now we have to identify the boundary or initial conditions. The ends are secured. When you secure the ends, what do you mean by this one? The displacement at both the ends are 0. So u is 0, u of x is 0, isn't it? In the beginning stage it is 0, x is 0, 0 comma t is 0, and u of l comma t is also 0. That is, displacement is 0 on the endpoints for any time greater than when t x is fixed, t is not fixed, right? Okay. And the string is released from rest. So initial velocity is 0, released from rest. Dou u by dou t. Dou u by dou t. When t is 0, initial velocity is 0 when it is released from rest, we have seen, isn't it? And the initial displacement is u. X initial stands that t is 0, which is x times L minus x. This is for our x. This is for all x 0 less than x less than y. Okay, now these two are boundary conditions and these two are initial conditions. That's the end of this problem. Thank you very much. We concluded this chapter. The next chapter we will solve these three ones. And obviously, what do you mean by this one? I will show you the first one. Okay, not this one. And I would like to give one more information, not about this problem. Laplace equation. U double x plus u double y is equal to 0. When 0 less than or equal to x less than or equal to a, and 0 less than or equal to less than y less than or equal to b. That is, the heat transferred through a thin plate, which is 0 to a in the x-axis, 0 to b in the y-axis. Now this is heat transferred through this plate, isn't it? The temperature u of x comma y at any point x comma y, what is the temperature? That is what we are going to find in this case. Okay? So here u stands for a steady state temperature. So we have nothing to do with this problem. Just I am giving an idea about Laplace equation. Steady state temperature in a rectangular plate whose vertical edges are 0, x equal to 0 and x equal to a, and upper and lower bounds are y equal to b and y equal to 0. Okay. This plate is insulated on these two edges. Insulated means there is no that is insulated. When you insulate, dou u by dou x when x equal to 0 is 0. In the right hand it's insulated, so it is dou u by dou x when x is equal to a is also 0. These are the boundary conditions for this problem. And whose upper and lower edges, this upper and lower edges, upper edge and lower edges are maintained at temperature f of x. So lower edge the temperature is 0 and for upper edge the temperature is given as f of x. That will conclude the boundary problem. So what is the temperature at u at x is fixed and x is not fixed, y is upper bound b, then the temperature is f of x. U of x comma 0, y is 0, then that is, so these two are initial conditions, the another boundary conditions of this problem, isn't it? So this is the Laplace equation. If you find u, here it will be steady state temperature at any point xy on this rectangular plate. So we will solve these three problems and find the u as a solution. We know u can be considered as x, y, a separable method, variable separable method, right? In this method, We will solve these three equations in the next chapter. Thank you very much.